Hello friends, welcome to Best Tutor. This is Rama Vishwanathan. In today's class, we are going to learn about rational numbers and irrational numbers. Rational numbers consist of all natural numbers, whole numbers, integers, decimals, fractions, square roots and cube roots of perfect squares and perfect cubes respectively. In the case of decimals, we have terminating decimals and non-terminating decimals. In the case of non-terminating decimals, we have recurring decimals and non-recurring decimals. How do we prove that terminating decimals and non-terminating decimals, which are recurring decimals, belong to the set of rational numbers? Let us get into the details of this. So, let us learn about decimal numbers. These are classified into two types. One is terminating decimals and non-terminating decimals. What do you mean by terminating? The term terminating states that the procedure will stop after a while. In the sense, if at all I have a decimal 0.125 and it stops after 5, the process of division ends at the step 5, then this is called as a terminating decimal. In the case of 0.13333 so on, the process of division is never stopping and the quotient 3 is going on repeating. Such a decimal is called as non-terminating decimal. Now, as we have discussed earlier, terminating decimals and non-terminating decimals both belong to the set of rational numbers. But we have already learned that a number belongs to the set of rational numbers if it satisfies three conditions. And the three conditions are: it should be in the form of p by q or a fraction where the numerator and denominator do not have any common factors. And the second point is both the numerator and denominator are integers, and the third one, denominator is never equal to 0. So now the challenge is to prove that 0.125 follows or satisfies all these three conditions. Let us check it in detail. (0.125) is a terminating decimal, and we can write this 0.125, the decimal number, as a decimal fraction, in the sense 125 by 1000. The power of 10 in the denominator depends upon the number of decimal places given in the decimal number. Here the decimal number has 1, 2, 3 decimal places. So the denominator should be a cube of 10, that is 1000. Now 125 by 1000, these two have a common factor 5, and as it is 25 also, it is going to be 25 by 200 or 1 by 8. Now 0.125 has got transformed into 1 by 8. This is a vulgar fraction, this is a decimal number, and this is a decimal fraction. A fraction is said to be a decimal fraction if the denominator is either 10 or a power of 10. Here 1 by 8 is called as a vulgar fraction because its denominator is not a power of 10. Right. So we have converted the decimal number into a vulgar fraction. Now, does this satisfy all the three conditions of rational numbers? The first one, it should be in the form of a fraction p by q. Yes, done. The second one, both the numerator and denominator should be integers. 1 and 8 both are integers. And the third one, denominator should never be equal to 0 and 8 is not equal to 0. So 1 by 8 is a rational number. Hence, we have proved that 0.125 is a rational number. This shows that all terminating decimals are rational numbers. How about non-terminating repeating decimals? Let us consider an example. 0.133 so on. It is a non-terminating recurring decimal. What is the notation of a non-terminating recurring decimal? If at all I have 1.323232 so on, Here the recurring part is 3, 2. So I would like to write it as, represent it as 1.32 with a bar on the digits which are repeated. So it's going to be 1.32 bar. If at all we have 2.3568, 3568, so on. You don't have to put the bar on all the digits. You can put the dot, a dot on the first and the ending of the repeating decimal. That means the first digit and the last digit of the recurring part. So it's going to be 2.3568, where 3 and 8 carry a dot above them, or 2.3568 bar. This is a notation of recurring decimals. Now how do we prove that this recurring decimal can be expressed in the form of P by Q? There are two types of recurring decimals. One is pure recurring decimal and the other is mixed recurring decimal. What are those? If I have 0.2222 so on, this is called as a pure recurring decimal, whereas 0.32222 so on is called as a mixed recurring decimal. Here in the decimal part, along with the repeating digits, there is one digit which is not repeating. Such recurring decimal is called as mixed recurring decimal. If we consider this recurring decimal, the entire decimal part consists of only those decimals which are being repeated continuously. You can have it as 10.121212 as well. Such a decimal is called as a pure recurring decimal. 3.15666. From the above example, we can say that this is going to be a mixed recurring decimal. Right. Now, getting back to the procedure. Now, I have to prove that this is a rational number. The procedure is as follows. Let us assume that x is equal to 0.13333 so on. Let us consider an example of pure recurring decimal initially, and then we will move on to a mixed recurring decimal to avoid confusion. Let me assume that it is 0.333 so on. So now the decimal is x is equal to 0.333 so on. How many digits are repeating here? Only one. So I will multiply one digit is repeating continuously or recurring, that means reoccurring. I will multiply this equation on both the sides with 10. So we have 10 into x is equal to 10 into 0.333 so on. 10 into x becomes 10x. 10 into 0.333 so on becomes, because we are multiplying with the power of 10, the decimal has to move towards the right. How many steps? That depends upon the number of zeros here. It is 10. Power of 10 is 1 here. So only one step it has to move. So it becomes 3.333 so on. Right. So 10x is 3.333 so on. X is 0.333 so on. So I will write this equation below this. If you observe, in these two decimals, the decimal part is the same. So if I subtract this equation, 10x minus x becomes 9x is equal to 3.333 so on minus 0.333 so on. It becomes, the entire decimal part becomes 0 and 3 minus 0 is 3. So we have got 9x is equal to 3 or x is equal to 3 by 9. That is nothing but 1 by 3. So we have transformed this recurring decimal into a fraction. This fraction satisfies all the three conditions of a rational number. It is in the form of P by Q. Both the numerator and denominator are integers and denominator is not equal to 0. Therefore, this recurring decimal can be expressed as a fraction. So this is going to be a rational number. Remember that always a fraction should be in its lowest terms. Now, let us move on to a mixed recurring decimal. Let us consider 10.2 2, 5, 5, 5, so on. So this is the given mixed recurrent decimal. We have to prove that this is going to be a rational number. Let us consider x is equal to 10.255, so on. As we know, mathematics becomes very simple when we convert a complex question into a simple question. This is a mixed recurring decimal. Initially, I would like to convert it into a pure recurring decimal. What is the thing which is disturbing this decimal? Only 2. Had this 2 not been there, then it's going to be a pure recurring decimal. So to avoid that, to remove that, that means I have to move the decimal point towards the right one step. I have multiplied with 10. So we are going to get 102.5555, so on. So 10x is equal to 102.555, so on. Now this is a pure recurring decimal. How many decimals are being repeated? Only 1. So we will multiply this equation on either side with 10 to the power of 1, that is 10. Thereby we get 100x is equal to 1025.555, so on. Now observe 100x, 10x and x. 100x and 10x have the same decimal part. 10x and x do not share the same decimal part. Similarly, 100x and x also do not share the same decimal part. So we will consider 100x and 10x and perform subtraction on either side. Entire decimal part becomes 0. 5 minus 2 is 3, 2 and 9. So x is equal to 923 by 90. If at all there are any common factors, we have to cancel. 923 and 90 do not share any common factors. So this is going to be the fractional representation or rational number representation of 10.2555, so on. Yes, of course, this is a rational number because it satisfies all the 3 conditions. So we have proved that both recurring and terminating decimals, both the terminating decimals and recurring decimals these both belong to the set of rational numbers. So in today's class we have learned how to prove that terminating decimals and non-terminating recurring decimals belong to the set of rational numbers. That is, how do they satisfy all the 3 conditions of rational numbers. Thank you. Let's meet in the next class.